Thank you, Austin. So machine learning is becoming more and more integrated in our daily lives, from email spam detection to even giving you recommendations. One of the companies that can do this for you are Spotify. They can recommend you a song based on your prior listening habits. Other big players are also investing heavily. We consider the likes of Google, Microsoft, and Amazon. This indicates one key point. There's a big opportunity here for businesses to take advantage of machine learning to augment and improve their current services. One of those within Northern Ireland are Kainos. Kainos are a digital services company that have many clients, including the UK government. They're investing time and resources into various staff in order to determine the advantages of machine learning. I happen to be one of these staff, and I'd like to share with you my journey. But first, what are the goals of this presentation? The first is to give you an introduction and overview of my journey as a software engineer who had to blend machine learning capability to the point where I reached competence and needed the ability to have a say and make an impact. The second of which is to give you a basic introduction to what actually is machine learning, what are the core concepts, and one really interesting technique in particular that we'll talk about a bit later on. The last of which is a scenario. As a software engineer, I like solving problems, and taking the core machine learning skills towards a problem is what gets my blood going. This is what I love doing, and tricky problems just like this. But first, you'd like to know who I am. Well, I'm Jordan McDonald, and you have to look at my ugly face for about 30 seconds. So, I graduated from Queen's University Belfast with a master's degree in computer science. As part of this is where I got introduced to the idea of machine learning to do various different things, including glaucoma detection, which is an eye disease, pedestrian detection, and I had a decent bit of success with this process. Upon graduating, I joined Kainos. I introduced them previously before. Inside Kainos, there is a team, the Applied Innovation Team. It is their goal to ensure the company as a whole do not miss the next big opportunity, whether it be immersive technologies, something Luke's very much invested in, or machine learning. So my interests and this team goals aligned quite well. I'm going to tell you a story. Consider the scenario where a third-party company is producing pills for a health board. They're producing pill boxes with pills in various permutations. However, at the point of production, these are often 2 weeks behind the official health board's records. This is a problem, and it means on-site, a member of staff has to come and manually count these pills. This introduces human error, and this is where machine learning is at strongest. So how can we solve this problem? Well, we take that pill box, and at the point of production, we take a photograph. This photograph can then get passed into a machine learning process which can count the pills for us. So it's fast, it's automated, and takes away that human error. The technique we'll use to solve this problem is a convolutional neural network, and that's the interesting thing I mentioned earlier. For simplicity, you might hear me refer to it as a CNN. It's just a bit easier to say in general. So what actually is machine learning? Well, it's a type of artificial intelligence that provides computers with the ability to learn without being explicitly programmed. The key word here is learn. That means when it's presented with new data, it can adapt and make a different decision. This is the power of machine learning. So what are some of the core concepts? This has been touched on before in a previous talk, but I'll just overview it anyway. So what is supervised learning? Take this bowl of fruit. In supervised learning, you will assign a label to every item in your data set. So we could go through and say, this is our banana, this is our apple, this is our orange. And so in supervised learning, everything can be identified. Let's take these away for now. Pretend for a second we are teaching an infant how to identify different types of fruit in this bowl. Pretend they've never seen this before. So we might give them the banana, another banana, maybe one more, all slightly different, all of their own variations, but they're still bananas. We can say we are training this infant. But how do they know it's actually a banana? Well, based on features, the likes of color, its weight, and its texture and its shape. We could call this feature extraction. After a while, they become so familiar with what a banana actually is, they've generalized it. We can say they've built up a model in their head, which means when presented with a new banana, they can tell us this object's a banana. This is a trivial example, but it covers up a lot of the key concepts behind machine learning in a relatively simple way. I like to compare learning machine learning, or any technical topic for that matter, to a roller coaster. At first, there's a learning curve. It's hard, and it's tricky. There's a lot of concepts you wrap your head around. But after a while, once you build this foundation of knowledge, it gets easier. The bumps in the road are smaller. But sometimes, with technical topics, and especially machine learning, If you go too deep down the rabbit hole, you get twisted in knots. Machine learning now is at its most accessible. There's a lot of tools, and there's a lot of services out there that can do this hard part for you. So confusion, maybe you don't need it. So what are these tools and services? I like to say each of them lies on what I call a gradient of familiarity, from my perspective as a software engineer. The ones that be most familiar are the cloud tools, the likes provided by Microsoft and Google. These are very high level, and a lot of the complexity is actually hidden. So a software engineer could just use these as an API, and it's very simple and right up their alleyway. Right in the middle, we have libraries. These are things that extend the likes of programming languages that give you some machine learning capability. They're much more complex, but you can do a lot more interesting things. The one we're interested in would be TensorFlow, which is the one at the bottom with the crazy shape. A bit more on that later. At the far end of the scale, we have essentially the core algorithms. This is where I tell a software engineer, stay away. This is the point in that roller coaster where you can get confused. And a lot of this stuff you get for free anyway as part of the software service and libraries. And there's an inherent trust there. There has to be an ability to accept that some of this is a black box, and that's fine. So I mentioned TensorFlow. It's developed by Google and uses the Python programming language. I'm not going to dwell too much, but what it essentially does, it has these things called tensors, which are multidimensional blobs of data passing between various operations. It lets you do a lot of interesting things, such as build an entire machine learning pipeline from reading data to executing our technique of choice, the convolutional neural network, and actually evaluating the results. So it's the tool that we chose to use to solve our pill validation problem. So the question is, where are we actually getting our data? This is a common question in machine learning. Currently, the pill production company does not have a camera in their process. So we need to think of something a bit more creative. How can we get around this issue? Well, we could keep looking for sources of data. Maybe we could crawl Google Images. We could use a general image data set like ImageNet. But this has problems. It introduces noise and introduces a lack of quality. Inside the Applied Innovation team, we have a creative environment. It is our goal to figure out innovative solutions. Ours was to use the Unity game engine tools. This gives you the capability of creating 3D models and many permutations of pills really quickly. So what does this actually look like? Well, like this. So we can have a large data set in minutes. This is really good, and it brings us closer to solving our pill validation problem. The question you might have, and I didn't realize at the time, is, can the artificial data set be used to solve this real-world problem? We'll come back to like bite me in the butt later on. The answer is maybe. We'll find out a bit later on. Pretend this is an image that we've captured from our data generation process. I'm going to use this to illustrate two things: what a convolutional neural network is in very high-level terms, and dispel some of the mystery behind computer vision. A computer does not see an image like we do. To illustrate this, I'm going to change a part of this image into pixel values. A computer sees an image essentially as numbers. In this case, black is typically represented by 0, and every possible color is represented by an arrangement of numbers. This is a simplified version of what it is. There's a lot more going on under the hood, but it gets the idea across. So say when we take our convolutional neural network, how does it work with its perception of an image? Well, the first stage is it puts what's called a mask on top of the image. As you can see, this perfectly overlaps with the pixel values. It's this guy's job to try and find features for us. In our case, can this thing find the pills for us? In this case, probably not. There's zeros, and there's nothing really you can infer from this data. So it can keep searching. And eventually, it might stumble on something of interest. In this case, our pills. But you might be wondering, how does this thing actually know it's a pill? Well, it's based on its features, such as edges, color, shape, texture, and size. And with TensorFlow, we get this feature extraction for free. This is where the black box mentality comes into it. We need to trust our program and infer it's getting the right features that we need to solve this problem. So we had our data, we had our tool, we had our problem, pill validation. We now needed a machine learning process that could solve the problem. So in TensorFlow, I built up a series of steps from reading data, performing our convolution, to evaluating the results. This is the pipeline. And the question you might have is, how well does this thing actually do? On our version 1 of the artificial data, well, the accuracy was 100%. This might seem impressive, but it's actually quite deceptive. An artificial data set, by its nature, doesn't have the variation of the real world. So I decided I would test this. I wasn't satisfied with this number. Could I make my artificial data set much more varied and make it much more difficult to get a score just like this one? So here we have like a really simple graph. We have the time it takes for our process to reach 100% accuracy. At the start, you can see it's really quick, it's really fast. But as I add more complexity, more variations, it takes a bit longer and increases in a fairly linear fashion. These things I call complexity could be like some positional variation, different types of pills. The one outlier jumps out here might be the doubled image size. But this is logical. If the image is twice as big, it'll take twice as many operations to find the pills. So it makes sense. And as a software engineer who values fast development cycles, I tended to stick to smaller images, just so I could experiment much more freely. So every node in this graph was 100% accuracy. So this is a bit more impressive. But we need to solve the core problem. We have our trained model. It's got 100% accuracy, but we need real images. So I use just everyday objects. I grab things, and as you see, this is essentially Skittles on white paper to represent pills. I made a small data set, which I could try to feed into my system. Would it still perform as well? Well, let's find out. Here's a bar just showing accuracy in general. Initially, it was terrible. This shows the difference between an artificial and real-life data set and the environment of the real world. Variations in lighting and inconsistent shadows change those pixel values, which I showed you earlier, that affect this process just enough to throw off our classifier. So I fixed this. I made the environment much more controlled, and it performed slightly better. So this is great. We're on the right track. So I did something a bit more drastic. The real world was controlled, and we had as good as images as I was going to work with. I threw away my artificially trained model. I started again. I created a data set that is much more complex, much more variation, and much closer to the real-life test set. So how well did it do? This is a lot better. This is a big jump. So I built on this success. I made the data set bigger again, and even more variation. It jumped up again. This is great. And you might think this story is going towards a happy ending. But in a lot of ways, this is the best result I could achieve. I performed many more experiments and many more tests, and they actually varied widely up and down the scale, but not exceeding this point. You might be wondering, why is this that was going so well? Well, it's this concept, overfitting. When a model learns the detail and noise in the training data to the extent it negatively impacts the performance on new data. Our training data is our artificial data set, our new data being the real-life images. So those changes in pixel values, however small or large they may be, was enough to throw off our classifier. Sure, it's okay, 80% accuracy is nothing probably to laugh at, but it's not good enough. We need to do a lot better. So how can I solve this problem? Well, I research. There's research papers and there's articles that actively tackle this problem. It's under the scope of what I call transfer learning. And there's a few that I've spotted that I'd like to dive into in the near future. Second of which, maybe we could just chop off the things causing the issue. Maybe the artificial data set needs to go. We could collaborate with this pill production company, get them to add a camera at the end of their process. And that's the process we're actually starting right now, and communications and dialogues opened up. So what have you got from this talk? You've got a bittersweet ending. Bitter in the sense, while the problem has reached a lot of progress, it has not actually been solved yet, and it's still ongoing. Sweet in the sense that you've seen what it takes to grab a software engineer, add on layers upon layers of machine learning capability. One thing I'd like to say about this stuff that I'm working on, this presentation in particular, that I've told people, and they're probably fed up of hearing it actually, is if I had to show everything, it'd probably take me about an hour and a half. So this is a very distilled version. So if anybody here would like to hear more about this journey, more about the things I tried, I'd love to hear from you at any point. I would like to extend my thank yous to a few people in particular at Keynos, Luke McNeese, Tom Gray, and the Applied Innovation team for making this talk a possibility. Thank you very much. Thank you.